Okay,
Oops.
got it. Okay. All right. So today I'm going to present some of my postdoc work. We're mostly working with my postdoc mentor Mason Porter on opinion models. So for opinion models, this is like a relatively new topic, at least like in the mathematics community, right? Compared with many other topics that have been traditionally studied. So here for today's talk, I will try to give you not only like one project I'm working on, but also some introductions like in the general field. And so hopefully after today's talk, you will believe me, there's a rigorous map behind those like opinion models in social science. And so here, should do this.
Maybe you can take the PDF once.
Yeah.
Oh,
Yeah. Just click on that once.
Yeah.
Okay.
so here, like the study of opinion dynamics kind of stands at the intersection of networks and dynamics. And so for during the 20th century, the study of networks in the form of a graph theory or the generalizations of graphs have developed into a substantial body of knowledge. And there are many applications, and such as social networks, which I'm going to talk about a lot today, and also food web, brain networks like the neurons, like in the brain, how they are connected. And so networks itself is interesting enough, but here we like to put some dynamics and combine these two topics. And so here are some of the dynamics that can occur on networks, such as opinion models or diffusions. Diffusions on networks. We can use this diffusion to talk about like disease spreading or news spreading. And random walks, also games, couple oscillators, etc. So usually the connections can be made in two directions. From the given the network structure, people are interested in how the dynamics would involve, right? So how long does a dynamical process reach its equilibrium, and how would the equilibrium look like? And also, if I suddenly see a emoji goes viral on the internet, is it possible for me to identify the critical moment that the one specific note, for example, or one specific moment that really promotes the spreading? And also like we can make connections from the opposite direction. So if you give me the dynamics of some agents or nodes on the networks, can we infer or try to find some connectivity over the network structure? If I observe some highly correlated dynamics, then does this really mean there exists like a link between these two nodes? Not necessarily, because it's possible to have a third node that connects these two nodes. And so here in today's talk, I will focus or try to explain some of the problems in the context of these opinion models. I will introduce you some modeling work of one specific type of model that takes into account some historical dependence of the opinions. And we can use that to explain, like, for example, like how stereotypes would affect the opinion formation. And then after that, I will provide you some analysis of such a model. So here comes the short introduction of opinion dynamics. Right? So the study of opinion dynamics models the opinion evolution as dynamical processes on a social network. So on a social network, the nodes would encode some social entities, such as humans, Twitter accounts, countries, etc. And the edges will encode the relationship between those nodes. It can be some Facebook friendship, or it can be like people who have received the same email or some other professional relationship. And then, so for the network structure will play a non-trivial role in affecting the overall dynamics. And then for some of the models, the dynamics in turn will affect the network connectivity. And so in today's talk, I will firstly show you some modeling work of opinion dynamics to use this random walks on networks to mimic social interactions, and we can derive a governing equation of the opinions from the some probability distribution. And then after that, I will try to answer the question, right, how the network structure would affect, how would it affect the dynamics. So here the structures of network, including both the topological structure as well as the temporal structures. And then after that, I will try to make some extensions with some existing work, and also point out like a few like directions of the open problems. Okay, so in the first part of my talk, I plan to answer the following questions. I've spoken a lot about this models of the opinion dynamics. So what are they? And then also, how can we use these random walks on networks to model these social interactions, and what are the governing equations? And then for some of the models, are we able to introduce some sort of like approximations using like a scientific computing tools to simplify the model? We will get back to the answers of these questions later. Okay, so here, this is like the general picture or the description like of the big picture of those opinion models. So here, like we have a network, and each node on a network will hold like a time-dependent value. It can be discrete, or it can be a discrete value or a continuous value. And then, so supposedly each agent can only interact with its neighboring nodes. So here, the network structure will put some limitations or restrictions on how this node would interact with other nodes here. And then here, like maybe at each time step, we take a pair randomly, or we choose them like deterministically, and then they would interact based on some governing law here. And if you're from like the kinetic like community, this may look similar to like the collisions of like the particles, and then you will have like some velocity or position before collision, and you have some the quantities like after collision, right? So here, the same thing goes to those opinion models, and the only difference is we will have the underlying network structure that adds on some restrictions of how the dynamics will evolve. And also, sometimes we can consider the group interactions, right? So usually in this, people use hypergraphs to model those interactions that involve like 3 or more agents. And I can look at like some collective group interactions between those nodes. And then after a group collision, I have some updated opinions. So there are basically 2 big families or categories of opinion models. So the first category is discrete valued models. So the most popular one is each node will take a binary value. So people either vote yes or no, true or false. And then there are models that such as like voters models. And this is a really good review on paper about like all different kinds of voters models. And we also have like this contingent model, like a social contingent model, which is something we hijack from the disease spreading models. And then like within this family of discrete valued models, people can introduce different levels of approximations, like node-based or degree-based. So degree-based that means we assume all the nodes that have the same degree value can be described, or their opinions, they can be described like by one opinion density, right? And then also on the mean field approximation. And within the family of this continuous valued models, we have some big group models on FJ or bounded confidence model. But here, I will like to come back to like these models later. But here, for all of these models, they are all Markovian. So which means they only consider or take into account the current states of the opinions, and without explaining some and are unable to explain like the systems that have some non-stationary or non-Markovian effects. And so here in the following, I will try to present you a model like of opinion dynamics that are derived from random walks on the networks, and such that you will see like the history dependence will just come up naturally in my derivation. Okay, so here is the introduction of random walks and waiting time distributions. I will consider a weighted graph called G, and it has the set of vertices and or the set of nodes, and also this Aij or represents like the identity matrix. And then I'm going to define random walks or n independent random walks on this network. So here for a node will stay, a worker will stay on the node until it makes a jump. But then here are two factors that determine like the jump of a node is one and when this worker will jump, and then to which node this worker will jump. So here we say originally like if this worker stays at node 2, and then the waiting time before this worker makes a jump follows this waiting time probability distribution, and we call it the waiting time distribution. Right? And then so here, according to this distribution, the worker will make a jump. Here. And then the next question is like which neighboring node this worker will jump to. And so here we make this node, the probability jumping to node J is proportional to this weight here. So then at a time step, maybe T1, right? So this worker will jump to a node here, choosing by this the probability here.
Excuse me, so the normalization for Aij tilde is the sum over all neighbors?
Yes.
That's the normalization.
Yeah. So here, like for this Aij, it represents the weights starting from this node I, but to all is like a neighboring node. And then here I'm like have like a normalization or a row of normalization to make sure like this the sum of this Aij tilde is always 1. Yeah, and also like feel free to interrupt me anytime and ask questions. And then so in the next step, this node like if we see this node 3, then it's gonna make we know it's gonna start here, but the time between this node 3 makes a jump is gonna be a random variable following this waiting time distribution. And then in the next time step, it makes another jump and choose between the neighboring nodes of this node 3 and keep doing this. And then so you see here, like this is like a one trajectory of this random process, right? And at each time step on this worker will make a decision on like when I will make a jump. And then the next decision is to which node I will make such a jump. And we can use like this random walk processes to model the social interactions between nodes on a network. So here is how it works. So for each agent on this social network, we'll follow the random walk processes Wi, and this Wi will govern or tells this agent when and who this agent I will interact with. And so here we put the simple assumption is if at time t, this worker jumps to a new node, then I will let this agent to adopt the opinions of that node. Right? So here, this is like a little diagram of a fully connected graphs like of 3 nodes, including like a self nodes. And then here I will have 3 independent random walks, and all 3 of them are resting at node 1, node 2, and node 3 here. And initially they will hold opinion values A1, A2, and A3. This is the initial setup. And then as time goes on at T1, so this node 2 makes the first jump, and it jumps to node 1 here. And then after it jumps to node 1 at this moment, it's going to look at what opinion this agent 1 is holding. Right? So at this moment, when this node 2 makes a jump, agent 1 is holding the opinion value of A1. So it's going to adopt the opinion of this X1 immediately and holding this opinion A1 until its next jump. And then if you look at this one example in this time step T2, then this worker one makes another jump to node 3, and then so no this agent 1 is going to take node 3's opinion, which is A3 here. And then here, like in T3, this one, worker 3 will make a jump, and then it jumps to node 2. And because at this moment, right, so for this agent 2, it is holding the opinion of A1. So after this jump, X3 will also become A1.
So are you assuming that whenever the random walk takes another time step, those times are distinct because they're simultaneous? There could be some funny things going on, right?
Yeah, so this is a very good question, right? So here, the question is like, what happens if you make some like a simultaneous jump, right? And so here, you're going to see later on, I do consider like this situation when all the agents will jump at the same time. And that's what I do is I will always take the left limit. Like if like a 2 nodes jump at the same time, I will always take the opinion right before the second agent jumps.
And it's also an assumption here that 2 agents cannot occupy the same node at the same time.
They can occupy
Oh,
the
they can?
same node. But here, like when they occupy the same node, it just means like 2 agents will just adopt the opinion
same
of the
idea,
same
yeah.
agent. Yeah.
So can you give some intuition about why there's a waiting time before the jump? Why is it not instantaneous?
So here, this is actually comes from some the modeling of the temporal networks. So people have studied or tried to just observe like the frequencies of some of the communication networks. And so historically, people assume like a Poisson statistics like between occurrence like of the edge, right? So that equivalently is putting like an exponential waiting time between those events. But then like later on, when people like try to really observe or collect data from real life, it looks like many of those inter-event statistics actually follow a Weiqi distribution. For example, like email communication and also the movie rental, etc. So which is kind of like makes sense is when you have like some earlier like interactions, right, and then it will lead to like a heavy tail or a long time of decay tail because you have future like interactions. And so here, like the idea of this project is to kind of like combine the information of like such modeling work. So if you wanted to try to specify or try to model the communications or interactions that come from like one certain way, and then you can combine like this model with the different distributions of the waiting times.
So your temporal, the temporal evolution there, right? That does not encode the network structure, does it?
It does not. So here, like for these the jumps were random variables, right? So they are completely governed by those waiting time distributions.
So do you assume that the network is completely connected?
So here the network information is encoded in the jumps, like which node you can jump to. So here, if you sorry, the other one.
And the AIJ, that is including like.
Yeah, it's just a little picture there, you know.
So even that
Oh.
AI to the.
Yeah, but when they, so the thing on the right though does not tell me anything about that time evolution.
But here is when you have this network information, you have different like probabilities of jumping to node 1 and node 3.
Yes, yes.
And here, this is just like a one trajectory of showing. Yeah. Okay.
Sorry, but it's not necessarily that you have a complete graph, right? It's possible for some of the nodes to be disconnected.
Yes. Yes. Exactly.
Can you give some intuition about why when they make a jump, they totally forget what opinion they had?
Yeah. So this is something I'm gonna come to later, like in the extension part. Yeah, I will get to that. Just don't leave the meeting and you will find the answer.
I wasn't planning on.
You said that they get grade 1.
Okay, and then so if we follow like this like a modeling work, then we can derive like the governing equation of this x. So here like this xi is the stochastic process, right? As I described earlier. And then so if I take expectation with respect to those like waiting time distributions, then I have this an expected opinion value xi associated like with each agent. And then I can derive the governing equation of this I satisfies this, which is an integral equation, and thus when this if the waiting time distribution is continuous with time, then I can derive like this is a differential equation. And so and here like for those phi theta, and they are all some related to this waiting time distributions, either by integral or Laplacian transforms. And so here, if we take a look at these models, and you can see in this one, not only it takes into account the current states of other opinions, but also it will incorporate its the history opinions like of this agent itself. And so this is we formally like we arrive at like these models, but then the next question to ask is your modeling valid, right? Like how can you validate like your choices of such a model? And so next I will try to relate or by considering like some common waiting time distributions and try to relate like this model with some existing model. And so the first waiting time distribution I'm considering here is a Dirac delta matter. Okay, I just show it. So here, like it says, I will the workers will always jump at some fixed time step. And so this is kind of like motivated like by the situations like when you will have some regular meetings, you will always like exchange your opinions at a fixed amount of time. And then if we plot the distribution of this Ti into the model, and we can simplify those theta, psi, and terms like in the governing equation and come to this governing equations. This actually is this decru model is actually a special case of this the Dirac delta induced governing equation here. And so P here is just like a constant matrix. And in our case, this P is equal to the A tilde that comes from the normalized agency matrix. And so Xn, n is like the time step. At each time you have like a constant transition matrix. And for the second situation is when you have an exponential waiting time distribution. So as I mentioned earlier, this corresponds to the Poisson interevent statistics and usually have a non-memory effects. And so this is the model. If we just plug this exponential waiting time distribution into the our governing equation, we will come to like an ODE system like this. And then this can be viewed also as a continuous version of this decru model like this. But this time we're going to have a slightly different transition matrix. And so here, like from these two models, and we can see when we select or make like this temporal networks on the edges follow this Poisson distribution, or when we consider like a Dirac delta, then we will arrive at the some models, some dynamics that do not have any history dependence.
So you have two disjoint distributions, one for the edges and one for the waiting time. So you have two disjoint types of distributions, one for the waiting time and one for the edges.
Okay, so here I only have in this model, right? I only have one to derive the model. I only have one family of distributions that characterize the waiting time distributions. But those waiting time distributions are usually related to the dynamics of the edges. Right, so here, like when we make the jumps between those nodes, you can either view it as some properties that are intrinsic within the agents. No matter where I jump, I will always follow my pattern of checking my emails. But also it can be some properties that are related to the edges. So when I make a jump from I to J, I will follow this distribution. But then if I jump from K to L, I will follow another distribution. So they are related with each other. And so then if we look at like a gamma distribution, gamma waiting time distribution, this is a commonly used to model like human communications, I think, earthquake, like a frequency, and also some pharmaceutical effects. And so here is like when the interesting happens. If we formally like plug this distribution like to our model, we can actually arrive at non-Markovian opinion models. So here you see for this one, this A tilde is still the constant of normalized adjacency matrix. But then we will have a damping term that will always drag this opinion to a historical averaged historical the historical average opinion of this xi here. And then so here this ki is like a kernel with like a decaying property. I think here for this certain setup, this ki is has like the exponential decay property. So this weighted average will always put more weights to its current or most recent opinions and less weights to the initial opinions. And then, so here, this model will not only consider like all the systems go to an equilibrium, but also it will force a person to maintain some self-consistency along the opinion trajectories. So this can be used to model people who try to maintain like a public image of themselves, or try use it to model, for example, like stereotypes. How would they like affect like the opinion evolution? And we also, as I mentioned earlier, there are also habitat waiting time distributions like in the temporal networks, and for example, log normal or parallel. But the thing is, as I showed you earlier, in the equations, right? Here are some terms like a theta or psi. They are related to this waiting time distributions by Laplacian transform. And so here, like for those like some habitat distribution here, even computing the Laplacian transform of this log normal function is non-trivial, right? So it is impossible for us to derive the governing equation explicitly. So here, instead of approaching it in a analytical way, I will try to solve the problems numerically. Instead, I will approximate like these waiting time distributions to use a sum of Dirac and delta functions. It's something here. So the basic or the idea is try to approximate this PIT based on using a sum of the Dirac delta functions, and this MKI will come from the original distribution. And then so this delta I represents the time steps. You will always make an opinion update of worker I. And then we can formally derive this and then arrive at this update like of this opinion models. Then this is like a extended version of this FJ model, like a special. FJ model is a special case of my model listed here. So at each time step, when we will like introduce a new opinion vector like into the pool of all the historical opinions, right? And then I will do like a renormalization of those matrices. So here for this P, it has an explicit like a formula that involves this MKI and also this delta I here. So at each time step, you will gain or have a new opinion vector xn, and then that xn will join the previous opinion vectors to form the next steps of the opinion xn plus 1 here. And so you see like here with the whole setting, one nice thing about this model is it is able to unite the many of the existing models, including like the Drew, Jensen, and also this the new non-Markovian opinion models. So this is like the first part of the modeling. Yeah.
So is that a higher order Markov chain, or is it like totally not Markov? Like if I took the x's and tried it as a big vector for the first n, I could get a Markov in the joint vector.
So it's got so this one, like, even if you write the whole thing as a vector, it won't be a whole chain.
Oh, it's still working.
Yeah, the reason is because here, like the weights are being normalized at each time step.
Thank you.
Okay, and so the first part is about modeling, and for the second part, I wanted to gain more mathematical insights about the model I just proposed. So can I do any like convergence or asymptotic analysis of this model, right? And then also earlier, I tried to investigate the relations between the network structure and the dynamics. Can I say anything of the right? And then also for those like waiting time distributions, how would the different choices of those waiting time distributions affect the dynamics? That involves not only the mean of those distributions, but also the time of the distribution. So here, before like I show you any theoretical results, I'd like to maybe show you some simulations to just give you some ideas like how the dynamics would evolve. So here I consider two different networks or two networks with very different community structures. So both of them have the same amount of nodes and also the same amount of here the expected total number of edges. So here, this is like a deterministic network from this Facebook. Here on the right hand side, I generate those edges of the net of the between the nodes, like according to like these two probabilities. And then so the expected total number of edges of this model is the same as this one. And then so here, and then I will run the different models like the two these two networks. So here for them, all these like distributions will have the same mean, but they they will have the same mean. And then here like each picture represents like the pinning trajectory. So for the pinnings will belong to 0 to 1, and then they will involve according to like different types. And then here, like when you look at the dynamics of course, they follow like a very different or interesting patterns. So here, for the like the Dirac delta one is more straightforward, right? It shows like those like the steps, right? Which is makes sense because you only allow them to make jumps at time 1. And so all of these distributions like have a mean of 1. So for a Dirac delta distribution, this means you only allow to make jumps at any time unit 1.
Trying to understand this graph. So each line is the opinion of one individual, one company.
Yeah, so each line,
They
maybe
change over time.
it's not very clear, like each line of the same color represents one agent of the painting.
So asymptotically, they all agree.
Yeah, so when time goes to infinity or really large, they will all converge to one cluster, which means they will all hold very similar opinions. Right? So in this situation, like we call it a consensus converge. And then also if you look at this uniform, and somehow it shows like this linear properties, right? And then this is of course like will make you curious, like why these things or these patterns are showing. And so then like when we start looking into this the problems or the dynamics a little bit deeper, and then so here is the true the theoretical results we have. So basically for this theorem, it states the topological structure of this network is actually determines the steady state solution, and regardless of what distribution it is. So here, suppose like this the renormalized this matrix is diagonalizable and -1 is not an eigenvalue. Then we can prove this steady state appealing vector x star always exists, and also it will follow the form of this. So where this VD is CD0, this is like an eigen decomposition with respect to this A theta. And then we will only keep the state whose eigenvalue is equal to 1. So here,
If there's no eigenvalue -1, does that mean the steady state, or doesn't mean the steady state solution if you need that?
so here, because we do a renormalization of this A theta, so A theta has like a row sum equal
Yeah,
to
I
1.
understand.
So it will always have an eigenvalue equal to 1.
I understand that.
Yeah.
But you say these steady state opinion, right? So that implies uniqueness, right?
Yeah, so it is unique, yeah. So here, or at least like from the theorem is if we have a unique decomposition, right, of it, this A tilde, then we have this convergence to this summation of the vectors. And so here, like the part I really want to point out is, you see at this steady state opinion, or the waiting time distribution do not play a role. So it does not like affect the steady state solution. So here, which is consistent with like our observation, right? You see at the steady state, they will always converge to like a value similar to a 0.5. But in the proof of one of the okay, so to prove like this theorem, right, we use eigendecomposition and this fixed point theorem. I'm not gonna talk about details, but here like one thing, one estimate or inequality like we found like in the proof is something like this. You will see like after we do eigen decomposition of this opinion, then this term can always be bound by some constant plus this phi t, right? So this phi t is related to the waiting time distribution here. And when earlier I point out like the uniform waiting time distribution, right? So here, if I know this waiting time distribution is uniform, then I can explicitly compute this phi t. And then this phi t happens to have like a linear profile. So then according to this bound, this explains like why we see the opinion trajectories have like a quasi-linear patterns. And we can do like a similar analysis for different types of distributions. And then, so here for these, this part of analysis, I only focus on like a homogeneous models. So which means I assume all the models will follow the same waiting time distributions. And then for the next part, I will just look at the heterogeneous models. So, but here, like when I say heterogeneous models, they are basically all non-homogeneous models. And there are so many different combinations of heterogeneous models, right? So I can have the walkers follow different waiting time distributions, or the waiting time distributions that can of the same type, but of like a different means. And so here I will only focus on like one specific condition when they all have this follow this exponential distributions. And then similarly, we can prove they will converge to the same steady state regardless of the lambda I, like the parameters in those exponential waiting time distribution. And then so here, when these are like the theoretical results, but there are more things I wanted to just try to explore and see if I can say more about those heterogeneous models. That's why we have done like some numerical simulations to further investigate this model. Right. So here, for example, in this example, I've shown what happens when you have like open-minded or stubborn nodes in your system. So here, when I say stubborn nodes, it means they tend to have a larger waiting time before the jump. Right? So they will listen to other people's opinions less frequently. Right? And then so we can see these nodes will actually have the power to drive the group mean towards their opinions. And also we want to see like how those the different types of waiting time distributions will affect the dynamics. Right. So earlier, like when people model the temporal networks and the statistics, and there is a debate like what type of distribution they should use, like if we should like use a heavy tail, and then between like different types of heavy tails, which one is optimal, right? And then so here, like this work is motivated by the such debate, right? So we wanted to see if different choices of those waiting time distributions will actually play a difference or affect my dynamics over here. And then the answer is yes, it does. For those like heavy tail distributions, they will slow down the convergence of my models. And also here, when I consider like a different the combinations of the populations, like of like the different types or have different population like either a 10% or 10%, sorry, 10% majority of nodes that following this exponential or follow like this a parallel distribution, will that make a difference at the steady state, right? And then so here I have come to and then just like by those such observations, right? So I have come up to some conclusions on how the network structures or how the waiting time distribution would affect the dynamics numerical conclusion. Right? And so here is the summary of my talk. Earlier, I have mentioned some of I have like a list out like some of the questions regarding this part. Right? And then so hopefully at the end of the talk, I have answered your questions. Answer like these questions. So the first part is about modeling, and in the modeling part, we want to see what are the opinion models out there, and how can we use random walks to model the social evolutions. And so here, like in the first part, I've introduced you how to use like independent random walks to mimic social interactions, and then how they are related to existing models. So basically, we can use one unified framework to explain different models. And then also for this one, when the waiting time distribution is non-exponential or have some heavy tail, then we are able to introduce the history-dependent kernel naturally to my opinion evolution. And this is something that naturally comes from the derivation of the model itself. And then for the analysis part, we have proved both the topological and the temporal structures of the networks can affect the solutions. But here for this topological structure, the eigen decomposition, eigenvalues, eigenstates will only affect like the steady state solutions. But on the other hand, for those temporal structures, like the waiting time distributions, actually can affect the transient properties like the opinion profile, like a linear or exponential, and also the convergence rate. And also we have observed like the existence of or presence of stubborn nodes, the nodes that have a longer waiting time distribution, or nodes that follow like a heavy tailed pattern will slow down the convergence. And so far, like I've introduced like one project, right? So of both like the modeling and analysis. And then next, I wanted to make some extensions of like this model and just talk about. And so in my there are like three perspectives to look at this problem or this type of problem. So one is from the view of mathematical modeling. This is usually like driven either by applications or by some phenomenon you observe from reality. Right, so for one of the work is one model is called like a bounded confidence model. So that project or model is motivated by some findings called the selective exposure in psychology. So it states that people will tend to interact with people who have similar beliefs as themselves and try to avoid the disagreement opinions. And then so in that situation, like to model such a phenomenon that people have developed this bounded confidence model. And so this part is really like driven by the application and what you can see like in real life, and how can you propose some like reasonable mathematical formulas to describe such a problem. And then so for the second part is like the analysis part. So this can be either asymptotic analysis or numerical analysis when you introduce some like a scientific computing techniques in this part. So in my today's talk, I didn't mention much about this analysis, right? But later I'm going to show you some works. Some of them have been done, and some of them are ongoing works, and see like how can we make such a connection. And then the third part is like to do some data-driven inference, because many models like in opinion dynamics, they the parameters cannot be measured directly in real life. How would you measure like the opinions of someone? And so and then I'm going to show you like some of the works I've done, and also how to extend like this current project to such studies. So within like this, for this, like, so here, for example, this is like one example of the mathematical modeling work I just mentioned on this confidence models on hypergraphs. And so here on hypergraphs, it consider like some group interactions, but also you can introduce like a different features to the model, like for example, a model with some heterogeneous properties, and also a model that incorporates random noise, or you may like include like a diffusion in your dynamics to represent some sort of like a self-thinking, like opinion, a self like an evolution process. And also like just from the modeling perspective of this current model, right? So one thing like we can extend is to, instead of considering n independent random walks, by selecting this Pij, we're selecting the jumping nodes based on some constant properties. I can make this to be probability that is dependent on the states. Right, so that goes back to your question there. But in this time, if we consider this Pij dependent on the states and also on the current values, so then the random walks, the n random walks, they won't be independent with each other. Right? So they will be like coupled in a way. So then this can explain like the two nodes, they will only talk to each other if their opinions are close enough, or when two nodes, they will only talk to each other when they actually arrive at the same node. And so for this analysis part, some connections I want to make. One is how when I say like asymptotic analysis, I mean like how can you make a connection between those many particle systems, like for a finite number of agents, and then you let the n go to infinity, and can you do some mean approximation, or like after you have the mean equations, how much you can say about like the relations between these two models. And then also here, this like for example, in this mean field approximation of this bounded confidence model, then the mean field density is governed by a kinetic equation of K type. And then so as the time involves, the opinion density, the probability will go to a sum of the Dirac delta measures, and will introduce some singularity. Right? So then if you want to compute that, how can you introduce some numerical methods, clever ways like to solve those problems. Right? And then there are some like other problems that are related to the project I just talked about. So one thing is, when I consider such a dynamics, how can you, is it possible to do or extend the current agent-based model to some continuum limit when your network like possesses some sort of structures, right? So here, especially in the model I just showed you, it has a kernel that comes from a history dependence, right? Is it possible to make a connection by utilizing that? Right, and then so for the third part is for data-driven inference. And so many occasions, like we are unable to observe some of the parameters and directly from the like a measure on the some of the values or opinions directly from real life. Right, so one reason is because people may have like, even if you ask people to fill in a survey, but maybe they have like a different scales from 1 to 10. Right, so when my doctor asks me, okay, from the scale 1 to 10, like how much pain do you have? I'm always confused, right? Like what measurements are you using here? And so that's why here for this one of the project I've done is try to infer like this social interaction from some partial observations. Right, so even though we cannot have observation of a continuous spectrum of the opinion density, but we can maybe observe some like cumulative effects. Right? And then how can we infer some of the parameters like in the form of functions from such an partial observation? And then also how much can you say about such an identification? Like can you like claim like the unique identifiability of such a inference? Right? And so the like the which is like a fundamental question in the inverse problem community. Right? And then so for the some extensions that go with the project I just talked about is to is it possible to infer those waiting time distributions like from the opinion trajectory? So here in this project, I try to approach a problem like using a density-based description. Right, but here, if I have the opinion trajectories, like in the agent-based dynamics, right? And then one natural question to ask is, can you, based on such information, and to do the inference of the network structure, right? And so this will be like a really interesting to explore. We now have gained like some information of the forward problems is themselves, and the next question is how much can you use those information or knowledge we have gained to try to solve the problem like, from the opposite way. Okay. All right, I think that's all for my talk. Thank you for